Now, there are various types of binary trees. Okay, so just to complicate things again. First, we have to define the definition of a strict or a full binary tree. Okay, which is a binary tree. Of course, we're talking about binary trees, which has degree of nodes of either 0 or 2, but not 1. Okay, so you can either have leaf nodes or full nodes, which has 2 children exactly. Okay, a complete binary tree is a full binary tree with all nodes pushed to the left. So you won't be seeing nodes or children nodes which starts at the middle. Okay, so all of the children nodes are pushed to the left. We also have an almost complete binary tree where instead of having a full node or or a node that has 2 children, okay, it has only one left one child at that node. And the perfect binary tree is a complete and a full tree where all leaf nodes are at the same level. Okay. Now, this is just the summary slide. So let's go into detail. Okay. So a strict or full binary tree is a binary tree where each node is either a full node, okay, or an empty or leaf node. So when we talk about a full node, it exactly has 2 children, meaning it has a degree of 2, okay? Where empty means it has no children, so it's a leaf node, therefore its degree is equal to 0. So as you can see, we have 3 different trees here on this slide. So first, on this one on the left, okay, this is a strict leaf or full binary tree because each node has either degree of 2. So A has B, C, B has D, E, D has H and I, or an empty or leaf node, okay, which are H, I, E, F, and G. Okay, so this is a full binary tree. This one as well, okay, so all the black nodes have degree of 2. Okay, so this black node has degree of 2. This node has degree of 2, and all the green nodes have degree of 0. So you can see here, there's no degree 1. There's no node that has a degree of 1. So that's the meaning of a full binary tree. Now you can also have a tree like this where the left child doesn't have a subtree, but the right child has a subtree. So that means this still falls under the definition of a full binary tree. Okay, as long as the nodes have a degree of 0 or 2, but not 1. Okay, that's the meaning of a full binary tree. So for every n leaves, okay, so let's say for this tree, we have 1, 2, 3, 4, and 5 leaves. Okay, a full binary tree always has a 2n minus 1 nodes. Okay, so here, 1, 2, 3, 4, 5, 5 leaves. That means the total, a full binary tree will have 2 times 5, which is 10 minus 1, 9 nodes in total. So this is 1, 2, 3, 4, 5, 6, 7, 8, and 9 nodes. You can also try this property on this tree. So how many leaves do we have on this tree? Okay, so how many leaves do we have here?
Two.
Is it just 2? Okay, I'll bring it down para makita natin.
Oh, is it 4?
Okay, so it's 4. We have this node, this node, this node, and this node. Therefore, how many nodes do we have in total? So total nodes, which is 2n minus 1. Okay. So how many total nodes do we have?
7, sir.
7, right? So it's 4 times 2, 8 minus 1, which is 7. So this is helpful. Okay, these properties are not there just to complicate things. No, let's say that you have a problem. Okay, which says basically it has the information that you have these number of leaves, and then how many nodes do we have in total? Even without picturing how the tree is structured, you can actually identify some answers to that. No, uh, so madaling maisip yun without even actually drawing the tree itself. Okay, but now since the figure is here, probably you were able to just count the nodes. Okay, but you can also rely on this formula or this property to easily come up with the answer to those questions, right? So yeah, that's correct. So there are 7 nodes. So 1, 2, 3, 4, 5, 6, 7. So we counted it here to verify that this property is correct. You can also do that here, but we're not doing it here on this session anymore. So just count the number of leaves. Okay, all nodes that has degree 0 or no children, and then apply the 2n minus 1. So you have an estimate or the number of total nodes in a full binary tree, right? So now the next type of tree here is a complete binary tree. Okay, so a binary tree, it's a binary tree in which every level except possibly the last is completely filled and all nodes are as far left as possible. Okay, so now we're having more definitions here. So again, completely filled. So the definition of full is if a node has exactly 2 child nodes or is a leaf node. So it's either degree 0 or degree 2. And complete is that the left child is filled first. Okay, so from here, you have A, left child is B, then we move to C. Okay, then if we go down, we don't start at C, but we start again at B, which is the leftmost child. Okay, so D, E, then we move to C, F, and G. Then if we go to the next generation, we don't start in the middle, we don't start at the rightmost, we start at the leftmost child, H, I, J, K, L, M, and O. Okay, so that's the meaning of complete in this case. So as long as the left child is filled first, okay, then we can push all the nodes as far left as possible. So here, this was our picture of our full tree on the previous slide. So you can play any node on the tree must have a degree 0 or 2, even though it's not the leftmost child. So that's okay. This is a full tree, but this is not a complete tree. Okay. On the other hand, here, we can see here that the leftmost child has children. Okay. But the other nodes here to the right doesn't have any children. So that's okay. This is still considered as a full and complete tree. Okay. Right. So as long as we push all the children to the left, that's considered as complete. Okay. Now it says here, except possibly the last. Okay. Again, because if we go here at the last tree, it might be a leaf node which are considered empty, okay, or we can have children on the last level. Okay, so now we also have another tree, which is what we call a almost complete binary tree. So it's a special type of complete binary tree. So the definitions here would still apply, except that the definition of complete, or definition of full, is, we can call it violated. Okay, so it's a special type of complete binary tree in which every right child has a corresponding left sibling. Okay, so if you are the right child, basically your family of nodes is full. Okay, you have the left sibling, but if you are the left child, not you, but the node, it's okay. If you have a left child, then it doesn't necessarily have a right sibling. Okay, so only the left child is defined. So if we refer to our previous definitions, okay, the full is a node that has exactly 2 child nodes or is a leaf node. Okay, complete, the left child is filled first. So if we look here, it's a complete tree since all the leaf nodes are pushed to the left, but not full binary tree because node E is not a full node. Okay, let me repeat that. Okay, so all the leaf nodes are pushed to the left, meaning when we reach the level 3 or the generation level 2, since this is level 0, this is level 1, this is level 2, and this would be level 3. Okay, all leaf nodes will be all the left nodes will be filled first. Okay, so the D is being filled first with H, then I. But for E, okay, only the left node is available, but not the right. Okay, so every right child has a corresponding left sibling. So node I has a corresponding left sibling, which is H, but not all left child has a corresponding right sibling. So the J, which is a left child, doesn't have a right sibling here. So this node E violates the definition of a full node. Okay. Again, a full node based on our definition here. A full node should have an exactly 2 child nodes or is a leaf node. So node E, okay, is not necessarily a leaf node, and it has 1 child node. So it violates the definition of a full node. So an almost complete binary tree is a complete but not full binary tree. Okay. Now you might be wondering why this tree is still here. Okay. So again, an almost complete binary tree is also a complete binary tree. Okay. So it still falls under this definition. Every right child has a corresponding left sibling. So I has sibling H to the left, K has sibling J to the left, M has sibling L to the left, and O has sibling N to the left. Okay, so it still falls under the definition of an almost complete binary tree, except that we have a special name for this, which is the complete binary tree, right? So yun lang yun. Okay. Now, last type of tree, which is the perfect binary tree. Okay, let me remove the annotate. Okay, again, andito ulit yung tree natin. Okay, so every non-leaf node has exactly 2 nodes. So B is a non-leaf node or an internal node. It has D and E. C has F and G. F has L and M. G has N and O. Okay, but so these non-leaf nodes. Okay, so these non-leaf nodes, okay, or internal nodes, has exactly 2 child nodes. Okay. There's one missing definition here, which is all the leaf nodes are at the same level. Okay, as you can see here, H, I, J, K, L, M, and O nodes are all at level 0, 1, 2, 3. They are all at level 3. That is what we call a perfect binary tree. So it's complete on both sides. It's also full on both sides. It's a complete and full binary tree, right? So if we have at every level D, okay, we have 2 raised to D nodes, okay? Same, it follows definition of the the generic definition of binary tree. Okay, remember kanina? Okay, at any level, okay, we have a 2 raised to d nodes. Okay, kanina it was actually 2 raised to L, right? But now we just changed the naming into D because we defined D as the level. Okay, and there are 2 raised to D minus 1 non-leaf nodes. Okay, so again, if you were given a problem, let's say a tree has 3 levels, okay, which means D is equal to 3. How many non-leaf nodes are there on the tree? Okay, that's actually a question. Okay, how many non-leaf nodes are there? If we have a full binary tree or a perfect binary tree, which has 3 levels, or D is equal to 3. Okay, how many non-leaf nodes are there?
Sir, would it be two D plus one? Yung formula?
This is the formula.
Oh,
Ito
sorry,
yung
sir.
formula natin. Ito lang.
Oh,
Ito yung
sir.
formula natin.
Okay. It's 7, sir. Yun ba?
All right, 7 because it's 2 raised to 3 minus 1, which is equal to 8 minus 1, 1 equals 7. Okay, so if we look at the graph or the tree here, okay, we just simply count. So we 1, 2, 3, 4, 5, 6, 7. So tama naman yung relationship. Okay, for we have 2D nodes at every level and 2D minus 1 non-leaf nodes. Okay, so we have 7 non-leaf nodes. So the total nodes would be 2D plus 1 minus 1. So where do you think this came from? Saan nanggaling si 2D plus 1 minus 1? Any clue? Or any hint? Ba't ako naghanap ng hint sa inyo? I know the answer, okay? Any idea saan nanggaling si 2D plus 1 minus 1 as the formula for total nodes?
Sir, kasi D is the number of like levels but the levels is only not including the first node. So but then -1 because when we use that formula it's usually pag 2 siya, I think.
So you think the -1 is the root itself? Tama ba?
Yeah, -1 since we're usually talking about 2 nodes, it would be 2 nodes, so -1, so minus the 1, and then plus D plus 1 since D is only the levels but then not including the parent level, so D plus 1.
Okay, you're almost there. Okay. Okay, let me give you a clearer clue again. So we have 2D minus 1 non-leaf nodes. Okay, 2D minus 1. And we have 2D nodes at every level D. Okay, and we know from this graph or from the missing definition here on the slide, the non-leaf nodes would be these nodes, and all, which would be the D minus from D equals 0 to D minus 1. So this is D equals 0. This is D minus 1. And this is level D. Okay? Kunwari, mahaba yan, tree na yan. Right? So, and the definition of a perfect binary tree is that all the leaf nodes are at the same level. Okay, so it's at level D. So if we have 2D minus 1, and we have 2D nodes at every level D, okay, how do you think did we arrive at 2D plus 1 minus 1? Algebraic expressions. Okay, see it na? Okay, sige. Let me give you the answer. Okay, so again, we have the 2D minus 1 for non-leaf nodes. So if we are counting this portion, the number of nodes here, this would be 2D. Oh, sorry. This would be 2D. Like, what? Okay. 2 raised to D minus 1. Tama? Is this correct? The non-leaf nodes, which is composed of D0 to D minus 1, the number of nodes there would be 2D minus 1. Tama?
Yes, sir.
Does everyone agree on that? Okay. Now, at level D, which is this one, we have 2 raised to D nodes. Okay, so this basically has 2 raised to D nodes. Okay, so total nodes, we simply add the 2. So we arrive at, okay, so ang kwento nito, the story behind this formula, so it's 2 raised to D plus 2 raised to D minus 1, okay, which is equal to 2 times 2 raised to D minus 1, okay, equals, which is equal to 2 times 2 raised to D, that's actually 2 raised to D plus 1 minus 1. Yan lang ang kwento niyan. Right? Do you follow?
Yes, sir.
Does that make more sense? Or do you want me to repeat it?
Repeat, yes, sir.
Repeat? Sige. Okay. Again, a perfect binary tree, suot ko na dito ha. Every non-leaf node has exactly 2 child nodes. Okay, dagdag ko na yung missing definition. And all leaf nodes are at the same level. Okay? Ayan yung definition niya. So every non-leaf node has exactly 2 child nodes, and all leaf nodes are at the same level. So in this case, you could imagine that the D here is equal to 3. So this is D0, D1, D2, and D3. Okay, or arbitrarily, we can actually define the last layer as level D, and all non-leaf nodes will be coming from D0 to D minus 1. Tama? Does that make sense? Okay, kasi all leaf nodes are at the same level. So you can't actually have leaf nodes at level D minus 2. Okay, because if that's the case, okay, so if I draw, this is D minus 2. Okay, so kunwari wala si H and I. Okay, for example, wala si H and I. So there's a leaf node D. Okay, then that already violates the definition of a perfect binary tree, because there's a leaf node, there's one leaf node which is not at the same level of the rest of the leaf nodes. Okay, or if we make it complete, okay, again, all leaf nodes to the left. Okay, let's say wala si N and O. So there's a leaf node at D minus 1 while the rest of the leaf nodes are at D. Okay, so that violates the definition of the perfect binary tree. Right? So kailangan lahat ng leaf nodes are at the same level. Okay? And that would be at the last level of the tree, which is level D. Okay? So ngayon, ang non-leaf nodes natin, the non-leaf nodes will be placed at all levels from D0, okay, from D0 down to D minus 1. Okay, again, because level D is reserved for all the leaf nodes. Okay, now we have this definition where the number of non-leaf nodes is equal to 2D minus 1. So basically, we can count the number of leaf nodes from level 0 down to level D minus 1. Okay, and that is equal to 2D minus 1. Now, if we want to know how many number of nodes are there at level, how many leaf nodes are there? Again, leaf nodes are all at the level D. So we can simply use this formula, okay, instead, to define the number of leaf nodes at level D. Okay, this 2 raised to D is applicable at any level. Okay, so don't get me wrong. If we want to know, let's say, how many nodes at level 2, okay, so level 2, this is level 1, level 0, this is level 1, this is level 2, then you can simply use the 2 raised to 2, 2 raised to D to know the number of nodes here at this level. Okay, so pwede naman gamitin yun doon. Okay, which will give us a 2 raised to 2 equals 4. So the D, E, F, and G, tama naman. But the thing here is, if we want to count the total number of nodes, okay, we have the formula for the number of non-leaf nodes, which are situated at D minus 1 to D equals 0 down to D minus 1. Okay, and we have all leaf nodes at level D. Okay, then we can simply use the 2D to know the number of leaf nodes. Okay, so kaya ngayon meron na tayong count for non-leaf nodes, may count na tayo for leaf nodes, we simply add them and this is the derivation of that formula. Okay, so basically in-add lang natin, okay, I'll add another text here, number of leaf nodes plus number of non-leaf nodes. Okay? Yun yung total nodes of the entire tree. Hello? Buhay pa ba kayo?
Yes, sir. That's gonna thanks, sir.
Okay. Yun lang yan. Number of leaf nodes. Again, the number of leaf nodes is equal to the number of nodes at the level D. Okay, kasi nasa last level yung leaves. Okay, plus the number of non-leaf nodes, which is 2D minus 1. Okay, so that's 2D plus 2D minus 1. 2 times 2D is equal to 2 raised to D plus 1 minus 1. Now, if we want to know the height of the tree, okay, ito nga, babalik tayo ngayon sa definition of height, which is the distance from the root down to the farthest descendant. Okay, so that means we simply have to get the D from this formula. Okay, so from this number of nodes, we simply have to define D. Okay, and that is if we if basically to get the D here, okay, we simply have to transform this exponent into logarithm, and then we arrive at this formula for the height. Okay, another algebraic exercise. Okay, so how do we arrive from this? N equals 2 raised to d plus 1 minus 1 to d is equal to log base 2 n plus 1 minus 1. Or actually, I think it should be plus 1. Pero sige. Okay. So from here, from n, okay, we take the logarithm. Okay, there's a property where okay, exponent. I say that's exponent. I think it's exponent or logarithm property where if a is equal to b raised to x, then x is equal to log base b a, base b of a. Okay, so transforming it, right? So magiging from n equals 2 raised to d plus 1 minus 1. Okay, we move the minus 1 plus 2 raised to d plus 1. We take the logarithm of the 2, or we basically just use this property. We arrive at log base 2 of n plus 1 is equal to d plus 1. Then we move the d, or we move the 1, whatever kaya na mag-isip. Okay, we arrive at log base 2 n plus 1 minus 1, so it's correct, minus 1 equals d. Okay, so yan yung kwento ngayon. So coming from this property where we have 2D nodes at every level and 2D minus 1 non-leaf nodes, we arrive at the total nodes of a perfect binary tree, where we simply add the number of leaf nodes and the number of non-leaf nodes. Okay, number of non-leaf nodes 2D minus 1, number of leaf nodes 2D. So we add both, we arrive at 2 raised to d plus 1 minus 1. Okay, and if we want to, and if d is the farthest level, then it should be our value for height as well. Okay, so if we want to isolate d, we use this process. Okay, we use this property to extract the d. Okay, so now from n equals 2 raised to d plus 1 minus 1, from this, we arrive at d equals log base 2 of n plus 1 minus 1. Okay, so if we are moving, if we make a path from a node to the root or vice versa, okay, the runtime will be at log n. Okay, don't mind this theta here. Okay, theta refers to loosely refers to the average runtime. Okay, if you remember our big O, it's the worst case. Okay, so theta is the average runtime, meaning it's in between the worst and the best case. Okay, so the average runtime would be a log n. So ganun lang yan. So if we traverse from root to leaf, okay, we always have to navigate a log n runtime. So with n as the number of nodes. Okay? So I brought the discussion back to algorithm runtime. Okay, from trees back to runtime. Okay, which is the big O or the theta log n. Right? Any questions so far?
Sir.
Yes.
So average runtime is just worst case.
No, it's not the worst case. Okay. Average runtime is okay. So the big theta here, okay, usually refers to average runtime. Okay. We say average here because we have no idea of the best case. So at on average, you can treat it as log n. Okay. But you can also treat it as the worst case if we have to traverse from the root down to the farthest leaf. Okay. So big O, okay, will still be log n. Okay, so big O will still be log n. So the worst case is equal to the average case.
Okay.
Yeah.
Thank you.
Formally, kasi, if you look at books, they would refer to it as big theta. And as basically just an FYI to everyone, this means average runtime. So it means it's somewhere in between the best case and the worst case. Okay. But for our class, we just talk about the big O, which is the worst case, and that's fine. Okay. Because big O is also equal to log n. Okay, so that means if we have to traverse from the root down to the farthest um, leaf, okay, so that's okay. But this one is the more formal definition kasi. Okay, but yun lang yan. FYI, theta means average runtime. Again, big O means worst case. Okay, worst case runtime. All right, any other questions? Okay. Now you might be wondering why this is important because later on we will discuss some operations on a perfect binary tree or on binary trees in general. Okay. So we clear the drawing. All right. So now we add that last property for binary tree. Okay. So the height is always equal to O log n or theta log n. Okay, because that will be the same. Okay, this is an important property of binary trees, which will be helpful later on for, when assessing the runtime of operations on a tree. Okay, so ito na yan. This is a summary of what binary tree is. We have the structure here. We have the properties here. Okay. And again, this is not 2L, this is 2 raised to L. Or yung kanina naman, 2 raised to D. Okay?